guys, we're going to study about the hysteresis loop, and this is the graph of the hysteresis loop. So B is the magnetic field, and H is the it is B is the magnetic density and or flux, but it is H represents the magnetic field actually, or you can say the current too, because the current is actually producing it, and hysteresis loop is fully based on electromagnetic and ferromagnetic materials. So you can say the current too. When we are going to increase the magnetic field, so magnetic flux or density is also being increased from point O to A, and then A will be like saturated point. But when we're going to decrease, it's zero. Like magnetic field is going to be decreased to zero. So it's the magnetic density or flux will go to the point B, which is which means that it is not going to the zero, but the H is already zero there. So B is a point which is known as the point of retentivity, which means it is a material ability to retain a certain amount of residual magnetic field when the magnetic force is removed. Like magnetic force is removed, it is also zero. It is also being zero, but it is still having some magnetic field. You can say some of that is removed, but it still is having. So it is the point of retentivity. So now point B to C. From point B to C, it's going to be zero now too. Like we, how it's gonna be zero? We are going to apply coercivity force. That is coercivity force means a force which is applied to the negative direction of H, negative position of the current. It's gonna be applied in it. So which is gonna cause H to zero and B to zero also. But now, if you're gonna apply its negative direction, so from point C to D, it will be the saturation point, but in opposite direction. Then E will be a point of the point of retentivity, but in opposite direction. F will be a point of coercivity force, but in positive, because here we apply the negative position, but here we get a point positive, so it will be positive, and then once more it will be the saturation. That's what's known as hysteresis loop. It's a full loop there, actually. Okay. So the phenomena of lagging of flux density B behind the magnetizing force in a magnetic material subjected to a cycle of magnetization is known as magnetic hysteresis. We mean lagging of flux density, like the flux density is being lagged there due to magnetizing force H. So this is full based on B and H. So there are four terms now: retentivity, which we study. It is a material ability to retain a certain amount of residual magnetic field when the magnetic force is removed after achieving saturation. Like then it is removed after saturation, now as we did. So residual magnetism or residual flux is like B point and a full B line on the y-axis. The magnetic flux density that remains in a material when the magnetizing force is zero. Coercive force: the amount of reverse magnetic field which must be applied to a magnetic material to make a magnetic flux return to zero. Reluctance is a position that a ferromagnetic material show to the establishment of a magnetic field. Reluctance is analogous to the resistance in an electric circuit. Now we are going to study about the soft magnetic materials, which are soft ferromagnetic materials are such materials that are easily magnetized and demagnetized. That can be easily magnetized and demagnetized. That's what they are going to use in uh, different materials, such as it is used in transformers. Okay, but hard magnetic materials are such materials which are difficult to demagnetize and magnetize. Okay, they're difficult to demagnetize, but are easy to magnetize, but are difficult to demagnetize actually. And magnetic flux density remains even magnetizing force is removed. So it will have the magnetic flux density there, even we are going to remove the magnetizing force even. So these are known as hard materials, which the examples of these are cobalt, tungsten, steel. But example of soft are iron and different more like silicon, iron are there. So it is a graph for hard ones which are having more. corrosive force they need, because more corrosive needs for to demagnetize, but it is the soft ones they need very less corrosive force to be demagnetized, so they can be demagnetized easily, and they are most useless then. So it was our full topic about the hysteresis loop that we studied today.